Hello everyone, my name is Subhrajit Bhattacharya. I'm an assistant professor at Lehigh University, and today I'll be talking about planning and control on Riemannian manifolds with boundaries. So this is the outline of the talk. The first part will be mostly focused on planning. So as the title says, it's planning and control. So I'll first focus on planning on manifolds. So this will be based on, this will develop on discrete search-based algorithms, and this this is in the flavor of this is the same as standard planning algorithms like A star and Dijkstra, and any angle path planning algorithms like theta star. But we'll see how we can develop a more formal approach to discrete representation of manifolds as a simplicial complex, and then develop an search algorithm, any angle type search algorithm using that simplicial complex representation. So this is a relatively recent work, but then I'll also talk about control on manifolds. So that's not that's not a very recent work. It's a joint work with Robert Greist and Vijay Kumar. But we'll see how some of the standard control algorithms that we understand very well on Euclidean spaces, Euclidean domains, can be generalized to manifolds, and in particular Riemannian manifolds with boundaries. So let me start with the first part, which is planning. So let's look at this picture. So this is kind of meant to serve as motivation for using a simplicial complex representation. So if we are trying to come up with a discrete representation of two sphere, the surface of a sphere, which one is a better discrete representation? Well, a graph, the picture on your left, that is definitely, it creates a lot of unnecessary holes, and it doesn't capture the topology, the shape of the manifold. But if you look at this picture on your right, that's a representation using a simplicial complex, and that is although it's a discrete representation, geometrically it's not exactly the sphere, but it is topologically a sphere, right? So it's capturing the topology of the underlying manifold correctly. So the definition of a simplicial complex is it can be described just as development on the traditional definition of graphs. So in graphs we have we have vertices and edges. So in simplicial complex terminology, these are called zero simplices and one simplices. But then in simplicial complex, you can also have higher dimensional entities like the two simplices and three simplices. So two simplices are these kinds of filled in triangles, and three simplices are this filled in tetrahedra. So as I mentioned, simplicial complex representation captures the topology of the underlying configuration manifold more correctly. So it doesn't create holes which do not exist, and it actually captures the holes that do exist correctly. So the idea behind motion planning on a simplicial complex as opposed to a graph is that in a graph, if you compute a path, the path is restricted to stay on the graph. But if we now represent our configuration space as a simplicial complex, then we can allow paths to go through simplices, right? Because that's now part, the simplices themselves are now part of our representation, right? So we can talk about points that go through these simplices. Previously in a graph, those points which are lying, say, inside these two simplices were not part of our representation. So the idea behind developing a search algorithm on a simplicial complex is relatively straightforward. It follows very much the same kind of approach as say Dijkstra search or A star search. So in those searches, what is done is you expand vertices, right? So you update what is known as G score of a vertex. Suppose that vertex is this vertex U. So suppose you have already expanded the vertices Q1 and Q2 in a graph, and now you are trying to update the G score of U. So if we or suppose we are expanding also Q1 and Q2 and updating U, right? I mean, it can be any one of that. So suppose we go from Q2 towards U, so that is taking that route from Q2 to U, we get updated G score for U. So here I'm writing with this D bar, but that's really what is known as G score in context of, say, Dijkstra search or A star search. And if you now go through a different vertex, say Q1, and find a better G score, you would update that, right? Better in the sense that it's lower. So that's what is done in graph searches. The idea behind using a simplex is to look at, in updating this G score, you look at not just the parent vertices, but you consider the possibility of this path coming through a simplex, right? So that's the dashed line that is shown. So what this means is you have to look at all the maximal simplices. So these are simplices which are not faces of any higher dimensional simplices in the simplicial complex. So you have to look at all the maximal simplices that are attached to that vertex U, and you have to consider the possibility of updating this G score based on a path passing through those maximal simplices. And in order to do that, we need an extrapolation algorithm. So we know the G scores of Q1 and Q2, for example. Here we are trying to figure out what will be the G score of U based on the dimensions, the lengths or cost of the edges that make up that simplex. So for that we need an extrapolation algorithm, and the idea behind the extrapolation algorithm is to embed this simplex in a Euclidean space, right? So the way we extrapolate this is by embedding the simplex in a Euclidean space, and then if we know the G scores, so everything is being embedded in a locally in a Euclidean space. So this the simplex is locally being embedded in a Euclidean space, and then we use the usual notion of extrapolation and straight lines in this embedding Euclidean space to kind of extrapolate the G score of U from the G scores of Q1 and Q2, right? So there are a couple of different extrapolation algorithms that we can use, but that's the overall idea. So the fact that we require the simplices to be embedded locally, being able to embed the simplices in Euclidean spaces is kind of the requirement that these manifolds be Riemannian, right? So the metric, the length of the metric that is resulting in this length of these edges in this discrete representation, the underlying metric be Riemannian. So that's where locally Euclidean metric comes in. So so that's kind of the condition, that's the requirement for being able to do this extrapolation. And so there are certain features. So this, if the flavor of this algorithm is in line with what are known as any angle search algorithms in this literature. There are few properties of this algorithm that are unique. One is that it's very much local, right? So it's just a vertex being expanded using only the information of its parents. So you have to look at not just the parent vertices, but the simplices attached to the vertex being updated, and but that's still a local information. So it only requires local information from going from parent to child, right? So it doesn't require long line of sight information as is required in some of the state-of-the-art any angle search algorithms like theta star. And this description of simplices, simplicial complexes, and their embedding in Euclidean spaces, local embedding in Euclidean spaces, these are well defined in high dimensional configuration spaces, 2, 3, 4 dimension, whatever dimension we have. It doesn't immediately address the course of dimensionality, which, like any say A star Dijkstra search algorithms, it's the same issue, but at least the search algorithm can be described. It's well defined, and all the properties of the search algorithm remain the same in any high dimensional configuration space. So here's a simple illustration of what it looks like. So here on the left you see this the progress of a search that is really the Dijkstra search, and here the paths are and this is showing this expansion of the vertices, right, starting from that initial vertex, and because this is a uniform triangular grid world, triangular discretization, this you see this hexagonal shape to this kind of the frontier, the wave front, or this is really the blue vertices are the open vertices in the open list that progresses, that kind of grows in all direction. So the paths will also be restricted in the graph, the hexagonal grid. Whereas on the right hand side you see the progress of the basic S star, the S star search algorithm that I just described. So S star is what we call this search in simplicial complex. So now paths can pass through simplices, and as a consequence, you can see that the wavefront is that grows from that center. Here the underlying metric is Euclidean metric. I should have mentioned that. So here the underlying metric is Euclidean metric, and you can see that it's a more uniform and aligned with the actual Euclidean metric, the wavefront grows. The growth of the wavefront is more in line with what you would expect with true Euclidean metric. Right? So I talked about the progress of this S star search, the star search in the simplicial complex, but I haven't talked about how to compute the path. And as with any search algorithm, there is a second step that you have to do in order to reconstruct the path. And the key to this doing that is to subdivide simplices as required. So once we have computed the g-scores of all the vertices up to the goal, and we are now trying to reconstruct the path, we have to kind of follow this gradient, kind of descend the gradient of the g-score. But in doing so, we have to take our path through the simplices, right? And in order to correctly do that, we have to subdivide the simplices through which this path goes through in order to get the correct path. And here are a few examples of in 2D environments where we can use S star, the simplicial complex star search to find shortest paths in indoor environments. It works also for non-uniform cost. So here is an example, simple example. As you can see, we get paths that are quite smooth, and the reason is that the path is allowed to pass through the simplices. So these points that you see make up that path, the kind of the waypoints that are created during this path reconstruction. These points can actually lie inside simplices, and that's why you not only get the a better path than, say, A star or Dijkstra, but also you get smoother paths than some of the standard any angle search algorithms. And we can also do this in configuration spaces where there is no obvious notion of line of sight. For example, in universal covering spaces of domains that let us find paths in different topological classes. So here you see two paths in two different homotopy classes. So these are shortest paths in different homotopy classes. And it naturally extends to three-dimensional domains. So here you can see the path in blue. That's the one found with S star search, whereas the red is the A star search path. And that's the blue one is it is closer to the true shortest path in this in this three-dimensional configuration space. But not only Euclidean three-dimensional configuration space, it works with configuration spaces with topologies that are more complex. So here we have a three-segment robot arm. So it's a three torus minus the obstacles, and we can use and it can have relatively complex cost functions. So this example had cost functions which are based on some energy consumption by the robotic manipulator, and we can see how we can get this kind of smooth transition, smooth paths connecting an initial configuration to a final configuration. And here is actually a picture of a manifold. Once again, we'll use a sphere, a two-sphere, and this just shows that the simplicial complex search, the S star search, finds paths that are much closer, but that are much closer both in terms of cost or length as well as in terms of smoothness to the true geodesic path, right? So here let me just show so here a few comparison with a few other methods, and the green path, the green plot that you see here is the true geodesic, whereas the blue curve that is kind of almost coincidental with the green is the path found with S star, and they're almost coincidental, and they almost match each other when the discretization becomes finer, right? So on the x-axis here we have fineness of the discretization, and that is the next slide, what the next slide is saying. So it can be shown that as this discretization becomes finer and finer, the error between the length of the path computed using the S star search algorithm and from the true geodesic path, it approaches 0 quadratically fast, right? So that's what we can prove that, and here is actually an experimental result that kind of shows that quadratically fast approach. All right, so the next part of my talk is about control on manifolds, and this is a joint work with Robert Greitzer and Vijay Kumar. So the idea here is that we understand control quite well in multiple contexts in Euclidean domains. So there are many control algorithms that work for which we can prove things, and it's well understood in Euclidean domains. How to generalize this to general manifolds with Riemannian metric and maybe some holes or boundaries in that manifold. So here is a simple illustration. So suppose we want to minimize the square of the distance, right? So suppose our robot is here and here is the goal, and we want to minimize the square of the distance to the goal. So that will give us a control algorithm that will take us to the goal, right? And in this case, because it's a Euclidean distance, we can write down this control algorithm in this closed form. A more complex example is in terms of coverage control, where we can have multiple robots and we have to distribute them throughout the environment in a uniform manner. And in order to do that, we minimize something called a coverage functional. So it's a function of the positions of all the robots, and it requires us to compute the Voronoi partitioning, and this is the coverage functional that we have to minimize. And the control algorithm is to follow the negative of the gradient of the coverage functional, and that once again you can compute that in a closed form, and this is what we get. And to summarize here, what this says is that for each robot needs to take a step towards the centroid of its respective Voronoi cell. So the key to generalize any of those algorithms, so both the control algorithms that I described were for subsets of Euclidean domains, right? Now the key to generalize this to Riemannian manifolds is to make this observation that in a Euclidean space, in a Euclidean domain, the gradient of this Euclidean distance at, say, say we fix the point Q, and we are computing the gradient of the Euclidean distance with respect to the point P, right? So this is partial derivative of the Euclidean distance with respect to the ith coordinate of the point P, and that is the same as the tangent to this line segment. So when I take the gradient, that becomes a vector. So that gradient vector is the tangent to this straight line segment connecting P and Q at the point P, excuse me. So that's the tangent vector. What can be shown is that this particular observation that we made holds true for general Riemannian manifolds and manifolds with boundaries or holes as well. So here we have this partial derivative once again, but not of the Euclidean metric, but this is the path metric. So path metric is a little more general than geodesics. Geodesics are well defined in its usual form on complete manifolds without holes or boundaries, but path metrics it's literally is the shortest path, right, that can go around, say, obstacles or holes on the manifold. So this is the partial derivative of that path metric, and that is this quantity right here. Well, it's a scary looking quantity here in the first glance, but if you look at it carefully, what this is saying is here we once again have this tangent vector, the components of the tangent vector, just as before. The only thing that we have to do extra is we have to multiply that tangent vector with the Riemannian metric So if you think of this as a matrix multiplication, so it's the matrix of the Riemannian metric that has to be multiplied with that gradient vector, right? So it has to be scaled by the Riemannian metric at the point P. So if at P the Riemannian metric is the matrix corresponding to the Riemannian metric is the identity matrix, for example, if the metric is locally Euclidean everywhere, then that is just multiplying by identity and we get back the same thing that we had before. So that's what the numerator. The denominator is just a scaling factor. So it's just normalizing it. So we want a unit. So we need a unit vector. So the gradient of the path metric is it happens to be a unit vector. So this is just making it a unit vector. That's it. So a little bit of a technical detail, and that is that this quantity here is not really a vector. It's not a contravariant vector. It's a covariant vector. So this is what is known as cogradient. So gradient. So there is a subtle difference, but it's at the end of the day, what really matters here is it's the gradient of the gradient of the path metric is it can be computed based on the knowledge of the tangent to the shortest path or geodesic at the point P, right? So the gradient of the path metric depends on the tangent to the shortest path at the point P and also the Riemannian metric at the point P, right? So if we can compute the shortest path, then we can compute the gradient of that distance function, right? So if we know the tangent and the Riemannian metric at that point, we can compute the gradient of the path metric. All right, so it was almost perfect, but there is a little technicality that we have to consider, and that is that comes with manifolds which have non-trivial topology, so which are not simply connected, for example, and that is with cut loci. So there can be suppose we are considering this point P over here, and there can be a set of points Q at which the shortest path connecting the point P and Q, the shortest path is not unique, right? As you can see, and both of these shortest path, both of them are shortest paths, and they have the same length, right? So the set of points Q that constitute the set of points where this shortest path is not unique, it's called the cut locus of the point P, right? And it's written with CP. Now the issue here is, of course, that at P, now if we are trying to compute the gradient of the distance to Q, that's not well defined. That's not unique. So there are two tangent vectors to the shortest paths, two possible tangent vectors, because there are two shortest paths, and thus the gradient is not well defined. And there can be situations. So in general, the cut locus is a set of measured zero, but there can be pathological cases where the cut locus can be sets that are not of measured zero, right? So finite sets of finite measure. So that here's a pathological example, and the other thing is this need not be purely determined by the topology. It can cut loci can arise due to high curvature regions. So suppose I replace this hole with a region of high cost, right? High metric or high curvature. So if this literal hole is replaced by high curvature domain, then we can once again have multiple paths that go around multiple shortest paths that go around that high curvature domain. All right. But at the end of the day, what we can do is, even in context of coverage control, we can generalize everything for these kinds of Riemannian manifolds with boundaries, and the coverage functional can be generalized in terms of path metric. So here we have replaced the Euclidean metric with the path metric, and the control algorithm can be computed based on that. So here we have those tangents, the path metric, and then there is the Riemannian metric appearing. Now this integral, the control algorithm, may look once again too complex in the first glance, but it turns out that it can be computed quite well in context of our while performing search-based algorithm like Dijkstra or basic S star. So the intuition behind this is that if you think of multiple robots which are distributed in a domain, say these are the three robots marked in green, you can run this Dijkstra kind of search. So this is a heuristic-free search. So it can be Dijkstra or basic S star kind of search, where we expand these wavefronts starting from these multiple robot positions. And as we do that, we create this Voronoi partition, as you can see in this small animation. We create this Voronoi partition, and during this kind of expansion process, this wavefront expansion and search algorithm, during the execution of that, you can compute this integral as part of that process, as part of that search process. So it can be computed efficiently. And here are a couple of examples on manifolds, a sphere and a torus with some obstacles on the surface of the torus. And as you can see here, the robots all started very close to each other, and they finally get well distributed throughout the manifold, and to minimize this coverage functional and attain coverage, uniform coverage of the entire manifold. So to conclude, we saw search-based planning algorithms on that can be described on simplicial complex representations of configuration spaces, and this allowed us to compute shortest paths or geodesics that are closer to the true shortest path or geodesic in the underlying configuration manifold. So simplicial complex being a more accurate discrete representation of that of a manifold let us do that. And we also saw control algorithms that are well understood in Euclidean domains can be generalized to Riemannian manifolds with boundary using this notion of path metric and geodesics to path metrics and tangents to those geodesics. Right? So that's where these two pieces connect, because the first part lets us compute these geodesic shortest paths in a correct manner, and the second part is where we can use those to compute our control algorithms. So that will be the end of my talk. The organizers of the workshop requested that I introduce the next speakers. So the next speaker is Dr. Maxim Likhachev, and it's a great pleasure to introduce Dr. Likhachev because he was my PhD co-supervisor when I was at Penn. And Dr. Likhachev is one of the leading experts in heuristic search and planning algorithms and their application to robotics. He is an associate professor at Carnegie Mellon University, and he'll be talking about planning for high-dimensional robotic systems by solving problems in low-dimensional manifold. Thank you.